Good afternoon or good noon. Welcome to IDEA StatiCa webinar, and today the topic is about how to design reinforced concrete beams and their details. At first, few organization details. We use GoToWebinar tool to make this happen, and please enter all your questions into the box or into the field you see on this slide. We will try to answer them through the webinar, and we will go or we will speak about them and discuss them at the end of the webinar. Today, I'm going to present together with my colleague Jana Kaderova. We are both product engineers in IDEA StatiCa, so maybe some of you already know us from help desk, or we had some online meeting, and it is our pleasure today to show you a few examples. So some or a few words at the beginning about IDEA StatiCa, because many of you maybe don't already have the software. So we have a huge variety of applications which are dedicated to structural design of concrete members, such as bridges, cast-in-place buildings, or even prefabricated concrete structures, as can be seen in the pictures. We aim to do just the checks and design of the details and so on. On the other hand, we have the newest application, which you will see today. It's called IDEA StatiCa Detail. This is application dedicated to the design of discontinuity regions, or maybe some of you say details, such as depth ends, hangings, walls, and many more. And we will go through one of these examples today. What this application brings to your table is that it can do ULS and SLS checks of these details. It has a code-independent method, but complying to the codes, and it gives you the possibility to see the results up to 15 minutes of your work to any topology, any loading, and in minutes. So you will see that we can keep that promise in the second example. When I'm speaking about examples, the first one will be in IDEA StatiCa Beam application, which is dedicated for the B regions or the standard checks according to the Eurocode and Swiss code. And later, my colleague will show you how to do the hanging of such I prefabricated beam in transport stage. So we'll go directly to the software. So let me change the application here. I'm in IDEA StatiCa Beam application, and let's start with the modeling itself. At first, I'll create a new project, and there is some wizard which helps you to go through the input process. It speeds it up, and you need to select a few things. So let me see. At first, I'm going to have a prefabricated concrete beam, not cast in situ, and there are two possibilities: the reinforced precast beam, which will be post-tensioned, or I can combine pre-stressing and post-tensioning. I'll use this option, but just because I need some construction stages, things I don't actually need to input the tensions itself. Right, so this is the biggest difference, that cast in situ concrete beam, or especially this reinforced concrete beam, does not have construction stages and, let's say, change of supports. That's why I will use this type, but actually I will design reinforced concrete beam. It will be a single span beam, which can be aligned at any surface. I won't do any haunches, so it does not matter which alignment do I have. On the next page, it asks me if I either want to design the beam in vertical plane, it means in 2D, is restricted, or I want to go for a full 3D modeling, Usually, for most of the cases, it's much easier to model in 2D. In this case, I'll want to include also the torsional moments, so I don't have any other option than to go for a 3D. And the length of my beam or the span will be 9 meters. On the next page, I need to specify the design codes. So as I mentioned, we'll use Eurocode. We are able to use a Swiss code. And the national annex, I will stay with the general Eurocode, but for you just to see, we have many national annexes and they are always up to date. So it will be some basic building, not a bridge, so I don't need to check these two checkboxes, and I'll just need to define the cross section. So I'll use some L-shaped prefabricated beam. And yeah, let me change a few things. For instance, the height of the flange will be 200 and the width of the web will be 300 millimeters like this. So you already see it here in the scene, and the material can stay as or the concrete grade will be C40/50. When I click OK, the cross section is applied. It asks me to input some basic load. So at first, I'll calculate the self-weight according to the cross-section automatically by the software. And I'll include some permanent load. It will be -5 kilonewtons per meter. And variable load, which will be -9. I will make it in more detailed way later. And critical load patterns does not mean anything in a single span beam. It helps you if you have multi-span beams to determine the critical load patterns. It means it detects the most unfavorable position of the loads, of the variable loads. So I click next, and there are last steps I need to do in my design. At first, I need to do I need to define the time axis of the beam. So for instance, I can go for a pre-stressing at 5 days, then storage yard at 7, transport at 25, and so on. And there is also a setting at which stage I would like to post tension if I would like. Then there is a set of the cantilever, right? So I'll show you how to do or how to display this setting. And the cantilever in the transport will be different. It can be 0.96 meters, and final supports will be at the ends, right? So 0 cantilever for final supports. And the end number, as it tells you in the tooltip, is additional internal support. It's used mostly, e.g. in the casting of composite slab. And once I hit finish, you will see that everything I defined in the tables will be modeled, right? So you can see here a 3D L-shaped beam with a span of 9 meters. I can type in some identifications about my work. They will be used in the report. So again, cross-section, which we defined, characteristics can be found here. Materials, members, if I want to include any haunch or add one more span and so on, it can be adjusted right now, not just in the wizard. Right, so supports, they can be seen like this. For instance, I want to fix also the rotation at another end, like this. And this is the setup we will use since the final support stage. When I go to the loads, I'm moving in the navigator, as you can see. So load cases, we have the increment for each construction stage for the permanent loads, for pre-stressing, and also we already made an input of some superimposed dead load and input of some basic load for for the variable load case, which is now set as exclusive, but the more variable loads you have, you can either set them to be exclusive like an envelope, or you can summation them as a standard load group type. So in this case, let me add a few more things, because I won't satisfy just with uniform distributed load. I'll apply also some point forces to the load case Q, and I wanted to show you how easily it can be done, because at first you need to define the intensity or the value, and then usually you define position like this. But it's very easy way, sorry for that, to define it by additional positions. So if I want to include it in 1/3, it can be easily done like this on one click. And I also want to include some point moments, because I don't want to include them on the eccentricity, so I'll include also some torsional moments. So something like this, value of 2.1, and it's global X like this, and in the same positions, right? So something like this. So if I go into the load cases again, you can see they are all defined in the same load case, and I have been able to define them very easily and very quickly. As I didn't add any more load cases, I don't need to modify combinations. I just want to show you that it's automatically generated for each construction stage, and you always have one ULS and 3 SLS combinations defined here, and it works under the code evaluation. It means it already applies the gamma factors, psi factors automatically based on the rules defined in load cases. The last two things to show you there is construction stages setting. So for a shrinkage, you can have some end of curing setting. If it's needed, maybe we'll speak about it later. You can turn on the nonlinear creep here. We won't use it, or at least I hope. And then the construction stage setting. So there are a few things which can be adjusted. So at first, let me show you how the beam will work. In uncoiled view, the green color always means that this part of the structure or the member is new. This is the casting stage. You can see it's in formwork, so there are no results for this stage. Then you have a transfer of pre-stressing, so you can see that the supports are at the ends. Storage yard, I defined this cantilever. At transport, you have different cantilever, then it goes back to the final supports setup, and then we have two service stages which are different because of the loads. What can be done here? For instance, the transfer of pre-stressing. I can either specify the time at which I'm introducing the pre-transition forces, or for instance, if I have what to be mentioned, it calculates according to the time the specific concrete strength based on the diagram from the code, or the prefabricator manufacturers, they know how to speed up the process, so they can use a specified concrete strength at this stage. So if I include like 30 megapascals, you can see that the time is calculated accordingly, and by this you can always do the analysis also for the members which are younger than 3 days, because you ensure this value based on the tests. Okay, so everything is set. I've modeled the beam, I have loaded it. All I need to do is calculate the TDA analysis. So now you see that it's calculating all stages. It calculates all the creep, shrinkage, changes of supports, all the increments of the loads, and in a few seconds we will have full results which we can explore. So like this. At first we can see reactions. at each construction stage. So as I mentioned, we can, this is at the formwork. Then we transfer of pre-stressing stage. So when it's going up the formwork, and so on and so on. And you can always see the prescription of the combination which gives you the extreme value. Then we have the results of the linear deformations, right? So again, you can switch the stage, you can change the deformation type, and so on. Again, the same principle. And for last time, it can go for internal forces, which may be interesting for us right now. So you can see that we will design the member for this bending moment. Okay, if we have these results, we can proceed to the actual design of the beam. So concrete design 1D part of the navigator, and we'll start in the data tab. Let me make this wider. So at first you need to define which checks will be done. At first, ultimate limit state, SLS. If we want to include some detailing rules, the detailed calculation of nonlinear deflection. So at first I want to show you some optimization. So I'll just try to speed up the process and do not calculate the deflection. I will tune it at the end. And this member is quite massive, and its lateral stability is assured by some lateral fixations in the thirds, so I won't include this check. It does not matter to me now. Then I need to set some exposure classes. They are mostly set for the crag width check and some relative humidity, which is transferred from construction stages setting. Right, so we know what we will check, and we proceed to the reinforcement tab, where we define two things. The first one is the reinforcement type. I can, for instance, use some zone templates and reinforce all the zones with the same number at once. Or I want to speed it up, and so I will use just one zone of the reinforcement, and I can adjust it or edit it by this button, or just clicking in the scene on the shape like this. And this opens the reinforcement editor, where I have two possibilities, or either to define the reinforcement by myself, or I can use a template if I have some basic type of the cross section, right? It's not defined from DXF file or anything like that. So it's quite known how to reinforce it, and I'll use the first template. Number of upper bars, it can be 2, and it can be 2 of diameters 20. Number of lower bars can be, let's say, 5, diameter 20. I'll use some edge bars, so they can be 2, diameter 12, let's say, and some stirrups, so maybe something like, yeah, this can be good. And when I hit OK, you can see in the scene that the beam has been reinforced. And for instance, I want to include 3 of these here. So you can see that it actually generated the reinforcement which I would do if I wanted, like, let's say, new from points, and it has been already defined on the cover, right? So you can see other webinars or our tutorials how to work with that. Yeah, okay, so let's see. When I click OK, you can see the reinforcement here. It applies to the whole zone. And the second thing I can define here is the check position, because for this type of the beams with construction stages, I need to define the checked positions. So let me check 3 of them. For instance, it can be like 0, yeah, sorry for that, 0.6 and maybe 0.9 or maybe 1 meter. And at the midspan, because this is the first critical section from the support because of the shear assessment here, and this one can be very interesting on the point of view of decreasing lever arm of in the section because of the changing bending moment, but still the shear will be assessed. There is no limit to the numbers of check positions, it just will take more time. So let's see what results will this setup give us and if we need to optimize or not. So in a few seconds it will do the analysis of all these sections, and yeah, we can see as expected that we does not satisfy at the end of design working life at the midspan. And I can see that we do not satisfy the stress limitation check at 115% of the unit check. And I want to know detailedly what's going on here. So I'll export it to the RCS software or application by a detailed icon, and I'll have everything here. And I can see that at the end of design working life, it doesn't satisfy. And I'll go through all these checks for you now. So at first, capacity, so you see the standard interaction diagram. We can see that it's non-symmetrical cross-section, so we have also non-symmetrical diagram. Then from the ULS, we have a shear assessment where you can see, yeah, we are at the midspan, so the acting shear force is 0. So maybe let me change for this one. So now you see the applied shear force, the resisting BW as the minimal width in the tensile area, and all the intermediate results which are used for the assessment that gives us this 11% of shear check, right? So let's go back to the midspan. So maybe the torsion. Yeah, you can see that it's based on equivalent thin wall section, and you can see the resistances of the concrete itself, the diagonal and the reinforcement, and then the checks also. The interaction check, right? So we check the interaction of shear force and torsion, and then shear force, torsion, and bending moment, right? Again, all the results, intermediate results, are in the tables. And then, yeah, I should go for the one which we don't know satisfy. So stress limitation check right here. And yeah, I see that it satisfies the quasi-permanent type. And thus I cannot help myself with the calculation of nonlinear creep, and I need to do something with the characteristic combination. And as I see, the problem is that it's tilted because of the non-symmetrical section, right? And it's very big in the compression fiber or compressed fiber, and I can help it with some redistribution. So if I add more reinforcement in the most effective area, I can help that. So I'll go back, use the reinforcement editor again, and modify. So by clicking to the scene, I want this one to change for 6 of diameters, and now I go for the results again. Right, and I actually see that it's like this. So I need to optimize once more. So for instance, I can use 7 of these, or maybe I can use 4 diameters here. And let's see the results. They are given in a few seconds. Yeah, it's the 104. So maybe we can see what's going on here. So let me just switch this off. So 104 stress limitation, and it's still here, but it's already minus 25, not minus 28.6. Sorry for that. So do not disturb. And we would need to optimize this as can be seen. So for instance, for the last time, yeah, let's say I will give 8 of them here. And for this purpose, I can also switch off the deflection calculation because we expect that everything will be correct now. So the deflection analysis will take some time. It actually goes from the results of the linear deformations, and then it calculates the stiffness along the beam and includes this change of the stiffness based on the cracked section, right? So yeah, now you see that we satisfy the check of stress limitation. We helped with the redistribution, and we could go through all the results again. If I want to see, for instance, deflection check, we can see that we are at the 71% of the unit check. It can be seen here. There's a total deflection which we assessed, so we can see the deflection, or the stiffness results can be interesting. You can see that it's cracked here at the midspan, so we have kind of efficient design because reinforced concrete is usually designed effectively when it's cracked. And I want to include all of these results somehow in my structural report. So we have 2 types of reports. One is the standard one, and then usually we go for a detailed one. So if I go for a detailed, it will create the report, and it can be modified in many ways right here on the right side, and you can see that it includes all the information you need about the project data, cross-section, materials, geometry, loads, and so on and so on, the results of the TDA analysis and the checks, right? So here are the checks which we went through, and at the end there is also some bill of material and data which you can send to your draftsman. And since the last versions, it can be printed either in PDF file or it can be exported to Microsoft Word .x file. So you can work with that and to modify it as you wish. All right, that's all from my part of the presentation. And now let's move to the second example. I don't know if you remember, is this hanger type of example, and it will be presented by my colleague Jana. So the word is yours.
Okay, thank you, Philip. I will make myself presenter, and while I'll be presenting my my example, please do not hesitate to send some questions to Philip. He will try to answer them, and we can have a look on some of those in the end of the webinar as well. So in my example, we will deal with IDEA StatiCa Detail. So let me start a new project. And this application is dedicated for those regions that cannot be easily checked according to Eurocode when the stress follows the assumption of the basic distribution. When we have some more advanced or more complex area that has to be analyzed in more details, you can use this application. And this is the case of my example. I want to model a hanger on a concrete beam. So I will start a new project. I will define the concrete grade and also the concrete cover layer. Let me set the 30 millimeters here, and you can see we have some basic templates for 1D members, for walls and diaphragms, but I will define it from scratch by general input. So new project will start. Ah, sorry, I have wrong screen. Okay, is it better now? Can you see the correct screen?
Yeah, we see the blank project in detail.
I'm sorry, yeah. So, my mistake. Let me start again. So this is the opening wizard when we define the concrete grade and the concrete cover. Here are the templates, and I just want to start the general input. And by the plus button, I can set the new entity in the project, which will be a 1D member. And here I will define the cross-section of this member. It will be the I section with hinged flanges. And I will directly set the dimensions, 60 millimeters of height, 450 the width of the flanges, and 1000 for the web, and 120 will be the width. Okay, I will press OK, and you can see I have short section. I can also define the trimmed end. For me, it will be on the right side. So this is the left end of the beam. So it continues to the right side. And I will directly make it a little bit longer because I will place a hanger here. The hanger will be added by the plus sign. You can see I have different table here, and I will choose from supports the hanging support. So now let me define the size of the hanger. So we will make it a little bit smaller. Okay, and the position of the hanger will be 1 meter from the end, and you can see that the warning disappeared because I have to be in distance from the end of my D region. So this is the D region, and I have to be far away from the border, which the application checks automatically. Okay, and one more thing, as the hanger will not, or the support of the hanger will not be perpendicular to the beam, I will add the rotation of the support, so you can see that that we also consider the angle in what the hanger will be supported. So once we have the geometry defined, we can continue to load. And you can see we didn't choose any template, so we have only one load case, LC1, which is permanent. And I will add some internal forces and load impulses. So let me define some line load, which will be minus 40 kilonewtons per meter on the top edge. And as a reaction, I will define some internal forces. You can see that I will define the internal forces in 1 meter from the end. So there will be shear force and also bending moment. And this is the left. These are the left values, and the values from right will be such 50 and minus 20 for bending moment. So you can see we are in equilibrium. The warning again disappeared. So this is the load case 1, and I will add another load case that will be variable. In load impulses, I will add a line load of -8 kilonewtons per meter. And again, I can see that I am not in equilibrium, which I fix by adding the corresponding internal forces at the section under the hanger. Okay, and once I'm in equilibrium, the warning disappears. So we have these two load cases, and to define some combination, I will add a plus combination sign. You can see that I have a new combination C1. This combination will be ULS, ultimate limit state, and I will just leave this combination rule as it is because I want to add two more combinations. So the second combination will be serviceability limit state and characteristic combination, and the last one will be SLS and quasi-permanent. And now I will edit the combination rules for all three combinations at once. So for the ULS, it will be 1.35 and 1.5 of the variable load. Characteristic combination will have the coefficients 1 and 1, and for the quasi-permanent there will be no variable load, so I will just enter 0 and it disappears. I confirm by OK, and you can see that my combination rules are here in the way I wanted them to be. Okay, and again, to speed up the calculation, we can deselect some of those cases. So if I just uncheck the load cases, they will not be analyzed in a separate. So I will have results only for combinations. And if you are interested, for example, for your first assumption only in C1 combination, you can also unselect these and calculate them in the second step if you want. Great, so we can now continue to define the reinforcement, and I will enter the input mode of the reinforcement. We don't have any templates here, so I will just enter everything from scratch. Again, by plus sign, I will add one group of bars, GB1. It will be the bars to the top layer, and I want there to be 2 layers, and the distance between them will be 50. And here I will just change the distance measurement between those 2 layers to minus, so you can see that the second layer will be below the first layer, not above. Okay, so these bars will be of 14 millimeters, and there will be 4 bars in one layer. Okay, great. So now let me add the reinforcement, the longitudinal reinforcement on the wall of the section. So I can either add new group of bars or I can copy it. There will be 3 layers, and the distance between them will be 300. We will have also smaller diameter of 8, and also only two layers of them. And now I want to shift them a little bit below, so I can increase the concrete cover. I will choose from settings to user value, and this value will be 170. So you can see I have 3 layers along the wall of the section, and the last one will be the reinforcement at the bottom. So I can just copy this group of bars, and I will change the top to bottom. And again, we have to change the measurement of the distance between layers, I will also increase the distance to 100. You can see it shifted, and there will be diameter 14 and 4 bars. Okay, and the last thing is to add some stirrups. So I will add a group of stirrups. These stirrups will have the diameter of 10 millimeters, and you can see I have already some definition. I can just show you how it works. So if I enter only one number, it means this is the distance of the first stirrup. Then, for example, I want to have some stirrups around the hanger in lower distance, and then the distance will increase. So I can either define the stirrups by the number. So let's say I want to have 12 stirrups and the distance between them is 150. So you can see 12 stirrups were added. And or if you want to have only the distribution by the distance, you can just define the distance between stirrups, and it distributes the stirrups along the length of the beam till the end. So we'll have 200 in the end. Okay, so I think that's all for the definition. We have geometry, we have load and reinforcement, and now we can continue and start the calculation. I will start by the check button in the top ribbon. So you can see only the combinations are analyzed. Now C1, then it will be followed by C2 and C3. And now we can see that all the load, it tries to find the equilibrium in each step of the nonlinear calculation. These are the short-term effects and long-term effects. And now we have the check of results, and we are finished with the calculation. And what we see are the overall results in the first step. So this is the figure that should tell you directly if you fulfill the code requirements or not, as well as this table. You can see also that we applied all of 100%, the 100% of the load, which is great because it means that the calculation is fine and the utilization is below 100, which is also fine. So we can display, for example, only the region with some higher compression. So the compression over 1 megapascal, and you can see it's only around the hanger. If I want to choose the SLS result, I will click to the corresponding line. And now let's go through the tabs with the detail results. So the strength tab corresponds to ULS code check. You can also see that C1 combination was taken into account. You can see the utilization of the concrete. You can see the highest stress is here under the hanger. And if I change the line to reinforcement, you can see that the reinforcement is utilized to 7% here. Okay, you can also display different entities. This is the utilization regarding the strain. Also, you can see it regarding to stress and like the exact values of stress and strain. And the same, of course, for concrete. You can display the utilization or the principal stress and some strains, and the direction also of the principal stress. Another ULS check is the check of anchorage. So you can see that we are close to 100% of the anchorage resistance, so it means that it's very well utilized. And you can also see the anchorage force here in each bar, and also the total force in the bar. And now we will move to serviceability limit states. So we have the stress limitation state here for concrete. You can see we are only on almost 12%, and also the stress limitation for reinforcement. Here you can see what combination was taken into account while evaluating this limit state. And to display the crack width, we enter the next step. And let me just mention that these values of the calculated crack width are compared to some limit value that can be entered here in the top ribbon. So if we want to be more strict, we can just change the value to 0.2, and you will see that these the ratio or the utilization changes, but we are still below 100%, which is fine. If I zoom in, you can see also the crack direction, and you can see that it's cracked around the hanger only as well. And the last thing is the deflection. Here, as I mentioned, sometimes it's a little bit tricky to display because it's a trimmed end of the beam, and it means we are not sure of the boundary conditions at the other part of the beam, so we do not really display the deflection, but we can see only the values here. Okay, and as Philip mentioned, we can export or we can display the bill of materials here, where you have all the rebars and a table, and also the report, which is generated by pressing the last button in the left tree. You can see that you can adjust the report as you wish. You can choose what pictures to display and what results. In my case, I have now all the results, so the report is quite long, but you can also display only some of those results. And the same as in IDEA StatiCa Beam, you can export this report either to document editable by Word or to PDF file. Okay, so this is the end of the second example, and let me ask Philip if we had some questions. We have a few more minutes.
Yeah, so let me start with the one regarding the detail application. The user asked either we can, or how do we assess the hanging or the hanger itself, the rebar.
Okay, so you maybe noticed that the results were displayed only on the part of the hanger which is in concrete. Yeah, so you can the detail only evaluates or checks the rebar, that the part which is in concrete, and not the part outside of the beam.
Okay, and then another user asks that they tried our export from the Beam application, and he's having trouble with the support at the bottom edge.
Yeah, so Of course, you can link these two applications together. So, for example, you have some longer beam that you check in IDEA StatiCa Beam, and then there's a hanger, and you want to import it to IDEA StatiCa Detail automatically. This is possible, but in such case, we had a little bit problem by the supports, because by default the wizard will put them on the bottom face, I guess, or so. But this, we know about this issue, and it will be fixed in the next release. So this link should work more fluently and in a better way.
Okay, and then we had also one question regarding Beam application, so maybe I'll try to answer that. As we already did. There was actually a question, either we check the indirectly supported beam when we included that reactions as a load, I mean the vertical forces and the torsional moments. We must confess that the Article 9.2.5 is not checked at the moment. So as we mentioned, a 3D analysis, it applied to a 3D TDA analysis, not the check of this 3D design of the whole structure. So we will consider this in our future development of our applications. As of now, maybe just a little reminder that we held a webinar about such L profile, actually in IDEA StatiCa Detail application and the study of transversal direction. Okay, so I think till now we didn't have any other questions. If you typed more of them later, we will go through them via the emails and so on. So feel free to type any. It's, I think, the last from the QA. Let me share the screen for the last time. And we can go to the last things, which we will do after the webinar. When we close this session, there will be a short survey. We kindly ask you if you have the time to fill it in. The feedback is always important to us, and we recorded this session, so we will process the recording, place it on our YouTube channel, and you will receive the link for that within 3 days. And if you are not the user and you find this software attractive, you can always apply for a free trial on our homepage, and you will receive one for 14 days, and feel free to use or to try. What not to forget, if you are already familiar with our webinars, then we have all of them in our resource center, so you can see the past webinars. And for the upcoming ones, we start already with the Connection Wednesdays. Some of you maybe know. So we start the first one on the 5th of September, and then consequently, each 14 days, there will be another session as you are used to, and you can see the next webinars related to the release of the new version in October. And this is how our resource center looks like, so feel free to go through all the tutorials, verification examples, videos, and so on, and explore everything that is inside of IDEA StatiCa. That's all from our side today, so we hope you enjoyed this session, and from me and our IDEA StatiCa team, we wish you the best of luck in your design and calculate yesterday's estimates. Have a nice day.
Goodbye.